All right, ladies and gentlemen, this class recording has begun. So, to get us started for today, as a little bit of review and as a starting point, I would like you to draw a picture for me on the back of the page that I gave you today where it's blank. I would like you to draw for me the Lewis structure for oxygen. Lewis structure for oxygen. Go. All right. Does your Lewis structure that you drew on the back of your page look like the one I have drawn up here on the board?
Yeah, no.
Doesn't necessarily have to look exactly like that, but the important thing is that it has to have how many valence electrons? 6. And that means oxygen is looking to do what in order to become stable? Pick up 2. So, luckily for oxygen, there's a hydrogen around. Okay? And hydrogen, atomic number 1, it's in the first column, it only has 1 valence electron. But is hydrogen a metal or a non-metal? A non-metal. Meaning, what is it looking to do valence electron-wise? Well, non-metals are looking to do what? Gain electrons. So even though hydrogen is in the first column and it has 1 valence electron, it is looking to pick up valence electrons instead of give them away. Specifically, 1 valence electron. Because remember, hydrogen's small, 2 is good enough for hydrogen, right? So if we have oxygen looking to pick up valence electrons, hydrogen looking to pick up valence electrons, what kind of bond are we going to form here? Covalent, right? So these two share, and we have a covalent bond. Okay. That works great for hydrogen, but what about oxygen? Okay, needs 1 more. So if another hydrogen was around, right, we could form that dangerous chemical dihydrogen monoxide, right? Yeah, all those bad things. We heard about it on Friday, okay? But another hydrogen isn't around. The only thing that's around is sodium. Okay? Now, you look on the periodic table and you find out that sodium has how many valence electrons? 1. Similar to hydrogen, except sodium is a metal, and that means it's looking to do what with its valence electrons? Get rid of them. Okay? So here, this comes here, right? Is everybody happy now? Yeah, everybody's happy, right? Remember, the ultimate goal of bonding is for what to happen? Lower energy state, right? And we do that by getting how many valence electrons? 8. Okay? Everybody ends up happy here, right? But let's look at it a little more closely. All right, that's what happened first, right? Remember, what did we say the line represents? Pair of shared electrons, right? That's the bond between oxygen and hydrogen. But, like we discussed, that works for hydrogen, but not for oxygen. But then, we have that sodium, and its electron, right, went from here to here. Okay? Wait, hold on. Nope, we'll go with that. Okay. All right, good? Good.
Does that line with the connecting the hydrogen to the oxygen represent one of the bonds to the oxygen?
Well, it represents one of the dots of the oxygen, but also one of the dots of the hydrogen.
Okay.
It represents 2 electrons that they are sharing.
Okay.
Okay? All right. Because sodium has lost that valence electron, what has it become? Stable, yes, but now we call it something. It is a... it's a... Not an anion, it's a cation. Because... Sorry, didn't hear it. Sorry. Did not hear it. Apologize. Okay? Did not hear it.
Hey, you didn't hear it, okay?
Alright, hold on, that's what we're doing right now. So sodium becomes a cation. It is now positively charged. Over here, though, sorry, let's do this. This oxygen and this hydrogen are bonded together. They are sharing 2 electrons. That makes them bonded together. They are a group now. But oxygen, even though it's part of a group, still doesn't have all the valence electrons that it needs. But once it gains that valence electron from sodium, it now has the 8 valence electrons to make it stable. However, if we totaled up all of the protons and electrons inside of those purple brackets, would it be the same number of protons and electrons? No. All right? When... Hold on. Yeah. That's my job. That's what I'm doing. So, when this happens, right? When we share these 2 electrons between oxygen and hydrogen, are we making any anions or cations? No. There is the same number of electrons and protons as there were before they shared as there are now after they're sharing. Sharing electrons doesn't create anions and cations. It makes 2 atoms attract to each other, remember, because they're like attracting protons and electrons with each other, right? But it doesn't create anions and cations. The number of protons and the number of electrons is exactly the same. But here, all of the electrons and protons within that purple bracket didn't all come from the oxygen and the hydrogen, right? This electron here originally was over here on sodium, meaning there are now more electrons than protons inside that purple bracket. Does that make sense? Yeah, good. Yep, there's only one more, but there is one more electron than protons, right? If we totaled up all the protons in this oxygen and this hydrogen, and all of the electrons that hydrogen started with and oxygen started with, plus that electron that came from sodium, we'd end up with more electrons than protons by 1.
Are we combining covalent and ionic bonding?
Okay?
Okay.
Now,
I thought you were just trying to do covalent bonding.
nope. That's the whole point of this, right? That here, this now has a negative charge on it, right? And what happens to negatively charged things and positively charged things? They attract, and we call that a what? What kind of a bond specifically? That type of bond, when this positive and this negative, that's an ionic bond. But here, this is a covalent bond. But at the end, how many valence electrons did everybody end up with? Well, Hydrogen didn't exactly end up with 8, right? But it ended up with what it needed, right?
It's happy.
Everybody's good as far as valence electrons is concerned, right? What's the main goal of chemical bonding? Why do atoms bond with each other? Pretty much, yes. Satisfaction comes in the satisfaction. It comes in the form of lower energy, right? Stability, okay? And that's caused, or that's a result of how many valence electrons? 8. So here, everybody has ended up with the right number of valence electrons, but, Jillian, like you jumped to conclusions, right, which is okay, which is what you're supposed to do, we actually combine both ionic and covalent bonding to get there.
So sodium's going to be negative?
Nope, sodium's positive, because it got rid of its valence electron, and then this group of oxygen and hydrogen were already joined together to begin with, but then they picked up another electron from sodium, so even though they're a group now, they still have a negative charge. So as a group, they can attract other positive things. Good there?
I get it.
And we have a special name for that.
That you said in the beginning.
We call it a polyatomic ion.
Yeah, that's what it is.
Front page of the sheet that we were just drawing pictures on. So, because you know English, you should be able to tell me 3 things about a polyatomic ion. Well, tell me one thing about a polyatomic ion. Rito, your hand went up first. There are many, that's one thing, right? And then the second thing is there are many atoms, polyatomic. Okay? What's the third thing you should be able to tell me about a polyatomic ion? It is an ion, meaning that it has a charge, a different number of protons and electrons. Could be more electrons than protons, could be more protons than electrons, right? Specifically, this here, right, is a polyatomic anion. Because what kind of charge does it have? A negative charge. This is a polyatomic anion because it's many atoms, right, joined together that have a charge. Right? So, now, hold on a second. So, Audrey, your question was?
So would the sodium be a polyatomic
So Audrey's question was, does that mean sodium is a polyatomic cation? And the answer to that is no. Why not? Because it's how many atoms? Only 1. Okay? So, this is just a cation, but it is not a polyatomic cation. It doesn't. Regular cations can combine with polyatomic anions. Polyatomic anions can combine with regular anions. Or polyatomic and polyatomic can come together. Or regular and regular can come together. Right? As long as one's positive and one's negative, they'll be attracted to each other. So in general, cations are attracted to anions whether they're polyatomic or not. Okay? They're anions, cations as soon as what happens? As soon as they lose or gain electrons, right? So as soon as this electron moves from sodium over to that oxygen, now we've created cations and anions. Okay? Because now now we have an imbalance here, more protons than electrons, and we have more electrons than protons. And that's what ions are. Good there? All right, so by definition, as we just discussed, polyatomic anions are a group of covalently bonded atoms that has, this is right underneath the title on the top left slide that I gave to you today. Sorry, this definition right here, underneath where it says polyatomic ions, right? So the sheet I gave you today, top left. No, that's your right.
Oh, gotcha.
Yeah. It's all right. I had to tell her. All right, so a group of covalently bonded atoms that has a positive or negative charge that acts as one unit. Okay?
The next slide is polyatomic ions too.
Okay. The next slide, okay, this is a table showing polyatomic ions. Notice when we look at all the elements that make up polyatomic ions, what kind of elements are they? Metals or nonmetals? They are nonmetals because polyatomic ions are bonded together how? Covalently. So that's why these are all nonmetals. To get these to form, we covalently bond. But now that they've picked up an extra electron, how do they bond to other things? They bond ionically to other things, but together they're covalently bonded.
So to make the polyatomic ions, they bond covalently, but to do anything else?
Right now, all of the atoms in here are stable because they've achieved those 8 valence electrons. But in the process, we've ended up getting a negative charge. So now they're attracted to other things that would be positively charged. Right? Remember, the ionic bond isn't necessarily a stable thing. The ionic bond happens because in getting stable, atoms end up with more protons than electrons or vice versa. Nina, go ahead.
Okay, so it's charged, so does that mean like the covalent bond is not charged, but on the one hand makes it not covalent, and then the other hand
The idea, yes, that will actually, the fact that it's charged makes them this, right? It makes them ions, all right? The polyatomic part means that there are many atoms that are bonded together covalently. But now that they've picked up some extra electrons along the way, now they are ions as well. Does that make sense? Okay, we'll see how it works here in just a second. Okay, oh, it's good.
Wait, so like once you've already covalently bonded and you already like all of the things are to their stable position,
Yes.
the amount of whatever the valence electrons they want, then you can never covalent bond at that ion.
At that point, yes, because if you have gained the 8 valence electrons, you're not going to bond with other atoms, right? Now, I will say that's a general rule. It's not always true, but that's a general rule. You'll find that in some cases, if you get more advanced, we have a situation that's called a coordinate covalent bond, where 2 atoms are sharing 2 electrons, but one atom provided both of those electrons. So I won't say never, but usually not. Okay? All right. Good with this so far? Yeah. Okay. Tonight, for homework, there's a little bit of reading to do and a couple of problems, but tomorrow we will spend a lot of time doing names and formulas for compounds that have polyatomic ions in them. We'll talk about how we handle that name and formula-wise, all right? I could, hold on.